Hi, we are Miriam Beiber and Victor Garcia, and we are going to present the dynamic logic circuits. This is the scheme for a static logic circuit that we are all familiar with. Basic CMOS static circuits consist of a complementary pull-up network, also called P-type, and a pull-down network, also called N-type. Here we can see an example of a static logic circuit with its corresponding pull-up and pull-down network. This circuit will be our example during all the slides. On contrast to static circuits, dynamic logic circuits rely on the use of a clock signal, and they only require either the N-type or the P-type network, plus 2 transistors. We are always going to work with the N-type network during these slides. Dynamic logic circuits, as you can see, use less transistors than static circuits, so less area is required. Here we can see the differences between the same logical function implemented with a static circuit and with a dynamic one. In static logic families, the pull-up and pull-down networks operate concurrently. On the other hand, in dynamic logic, the operation of the pull-down network can be divided into 2 major phases, the pre-charge and the evaluation phase. In what mode the circuit is operating is determined by the clock signal. Now we are going to explain both phases. First, it's important to define that the people's transistor governed by the clock signal is called the pre-charge transistor, and the NMOS transistor also governed by the clock signal is called the evaluation transistor. When we are on the pre-charge phase, the pre-charge transistor is on and the evaluation one is off, and during the evaluation phase, the state of the transistors is the opposite. Let's focus now on the pre-charge phase. When the clock signal is low, as we said, the pre-charge transistor is on, and the output node of the circuit is pre-charged to VDD by this transistor. During this time, the NMOS evaluation transistor is off, so the NMOS logic network is isolated from ground by a series of NMOS transistors. Now we are going to see what can happen during evaluation phase. When the clock signal is high, the pre-charge pull-up transistor is off, and the evaluation transistor is turned on. Depending on the values of the inputs and the composition of the pull-down network, a conditional path between the output node and ground is created through the NMOS transistors. If such a path exists, the capacitance at the output node is discharged and a low output signal is obtained. This is depicted in the case A of the slide. On the other hand, if this path between the output node and the ground does not exist, the pre-charge value remains stored on the output capacitor CL, and a high output value is obtained during the evaluation phase, as depicted in case B. There is a very important property of dynamic logic circuits. Observe that in case B, there is no possible path between the output node and VDD. Consequently, if the capacitor is discharged, it cannot be charged again. The inputs to the circuit can therefore make at most one transition during evaluation. Here we can see an example of how the capacitor is discharged during evaluation phase, when the 3 inputs are high, for the logical function of the example. We have already seen that dynamic logic circuits require less area because they require fewer transistors. This same reason adds another interesting property to dynamic logic circuits, and it is that the load capacitance for the circuit is substantially lower than for a static CMOS, and then faster switching speeds can be obtained. We can also analyze the disadvantages of dynamic circuits. As we have seen, in order to work with this type of circuits, a clock is required, what makes the design for these circuits more difficult. Also, it's impossible to operate the dynamic logic at low speeds. Dynamic circuits need to be refreshed, because output capacitor discharges as time passes. Another disadvantage is that dynamic circuits are more sensitive to noise and timing errors. Imagine this case, where C suffers a glitch during evaluation. During the glitch, the charge in the capacitor is discharged, and it cannot be charged again during evaluation, producing an error. As we have seen, a glitch can discharge the capacitors in the evaluation phase, but a delay between gates can also lead to mistakes. Let's see an example of what happens when cascading dynamic logic circuits. In the pre-charge phase, all the outputs of the different stages are loaded to 1. Now imagine that in the transition from the pre-charge to the evaluation phase, we change the input so that output 1 makes a transition from 1 to 0. As there is a delay between the two stages, at the start of the transition, the high value of output 1 will erroneously discharge output 2, as we can see in the figure. If output 2 is erroneously discharged, it will remain discharged for all the evaluation phase, because in the evaluation phase, VDD is not feeding the circuit. Then, output 1 will be 0, and output 2 will be 0 too, but actually output 2 should be 1. The solution of cascading dynamic gates is to use CMOS domino logic. After each stage of the circuit, we add an inverter to ensure that the output is low during pre-charge and prevent the next stage from evaluating until the current stage has finished evaluation. Pre-charge makes at most one high to low transition, while evaluation makes at most one low to high transition for each evaluation. Consider now the operation of a chain of domino gates. During pre-charge, all inputs are set to 0. When many stages are cascaded, evaluation proceeds from one stage to the next, similar to dominoes falling one after another. This type of circuits also have some disadvantages. For instance, the most clear now is that we need more transistors. To conclude, we are going to summarize the main ideas that have been commented in this presentation. As we said, dynamic logic circuits require fewer transistors than static circuits, so less area is required. Also, as there are fewer transistors, the input capacitance and diffusion capacitance are lower than in the static case, so faster switching speeds are possible. Also, we saw that glitches can produce errors in this type of circuits, so they are less robust because they are more sensitive to errors. Finally, we observed what happened when cascading dynamic logic circuits, and the necessity to implement domino logic in order to evaluate only one stage at each evaluation phase. And this is all. We hope that with this presentation you understood the fundamental of dynamic logic circuits, and if you have any questions, do not hesitate to contact us.